So we're still moving toward solutions to the Schrodinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrodinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic energy and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrodinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, I times E times T divided by H bar. So this is our time evolution part, and this is our spatial part. What does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi and its complex conjugate, I end up with the complex conjugate of big X as a function of position times the complex conjugate of this. And the only part that's complex about this is the I here in the exponent, so we need to flip the sign on that. And we'll have e to the I, positive I now, e t over h bar. That's for the complex conjugate of psi. And for the psi itself, well, x of x e to the minus I e t over h bar. Now, multiplying these things together, there's nothing special about the multiplication here, and this are complex conjugates of each other, so they multiply together to give the magnitude of, the squared magnitude of each of these numbers together, which, since these are just complex exponentials, is magnitude 1. So what we end up with here is x star x. Essentially the squared magnitude of just the spatial part of the wave function. There's now no time dependence here, which means the probability density here does not change as time evolves. So that's one interpretation of these, or one meaning of these things being called stationary states. The fact that I can write a wave function as a product like this, and the only time dependence here comes in a simple complex exponential, means that that time dependence drops out when I find the probability distribution. Another interpretation of these things as stationary states comes from considering expectation values. Suppose I want to calculate the expectation value of some generic operator, capital Q. The expression for the expectation of an operator is an integral of the wave function times the operator acting on the wave function. So complex conjugate wave function, operator, wave function. Now I'm going to go straight to the wave function as expressed in terms of x and t parts. So complex conjugate of the spatial part times the complex conjugate of the time part, which from the last slide is e to the plus I e t over h bar. Our operator gets sandwiched in between the complex conjugate of the wave function and the wave function itself. So this is again, no stars anymore, come on Brent, just x and then e to the minus I e t over h bar. And this is all integrated dx. So this is psi star, and this is psi. And this is our operator sandwiched between them, as in the expression for the expectation. Now, provided this operator does not act on time, it doesn't have anything to do with the time coordinate, and that will be true for basically all of the operators we will encounter in this course, has no time derivatives. What that means is that I can push this time part past the operator. The operator will not act on the time part, so that's okay. And what that means is, as before, these two guys will just end up directly multiplied by each other, excuse me, and you will end up with just 1 as a result. Integral of x star q hat x dx will be what results. Again, the time part drops out if, q has no partial time derivatives, which is true for basically all of the operators we'll meet. Position, x hat, that's just multiplying by x. Momentum, that has to do with differentiation with x. And then kinetic energy, that again has second derivatives with respect to position. There's no time derivatives in any of these physical sorts of operators that we'll be talking about here. What that means is that, again, the time dependence drops out, and the expectation value of this q operator, and q can be anything here, again, has no time dependence. So our expectation values are constant. If our physical system is described by a wave function that separates like this, then our expectation values have no time dependence. The next topic I'd like to address is the energy of a stationary state, which also happens to have a very nice expression. The spatial part of the Schrodinger equation that resulted from our separation of variables was something I call the time-independent Schrodinger equation. The time-independent Schrodinger equation, which could be written simply as the Hamiltonian operator acting on the spatial part of the wave function was equal to the separation constant times the spatial part of the wave function. H times x equals e times x, where h is now an operator, so I shouldn't say time. I should say the Hamiltonian operator acting on x is equal to the separation constant e time just multiplied by the spatial part of the wave function. So suppose I want to calculate the expectation of the Hamiltonian operator. Now the Hamiltonian operator, is related to the energy of the system, so if I calculate an expectation here, it should have something to do with the energy of the system. It's not immediately obvious that h acting on the wave function gives you the energy multiplied by the wave function, but calculating an expectation value like this makes the connection much stronger. So let's write out that expression. We have an integral, and then we have the wave function itself, x star e to the I times the energy times the time over h bar times our Hamiltonian, and then the non-complex conjugated wave function itself, e to the minus I e t over h bar, integral dx. Now we know the Hamiltonian operator, that has partial derivatives with respect to x and multiplication by the potential. So again, this operator isn't going to have any time dependence, same as what we reasoned when we were calculating expectation values. These time dependences drop out for the same reason here as they did in the previous slide in general. We're just left then with the integral of x star h hat x integrated dx. But I know this. That's this. So I can make that substitution. Knowing this spatial part of the wave function solves the time-independent Schrodinger equation allows me to simplify this. I just end up with the integral x star e x integrated dx. Now these x's are not coordinates, they're functions of the x coordinate, just to be clear about my notation. But this e now, that's just a constant. It can be pulled out of the integral entirely, and we're just left with e times the integral of x star x, should make it clear these are capitals, dx. And this, if we've properly normalized our wave function, is 1. So what that tells us is that the expectation of the Hamiltonian operator is our separation constant, E, that we got when we applied separation of variables to the time-dependent Schrodinger equation. The Hamiltonian operator is something we expect to be related to the energy, so it's reasonable to identify the separation constant E with the energy associated with this particular state. So now what this tells us is that the energy of the wave function, the expectation of our Hamiltonian is the energy of the wave function. Now we know there's some uncertainty in quantum mechanics, so is there uncertainty in our energy? If we actually measure the energy of our wave function, do we ever get E, the separation constant? Well, in order to calculate the uncertainty in something, we need to calculate effectively the standard deviation or the variance. Let's write it as the variance, the squared sigma sub E, where E perhaps now refers to the energy. So let me write this as sigma sub h hat. If we want to calculate this, what we have to calculate, well, sigma sub h hat squared, that's equal to the expectation value of h squared minus the expectation value of h quantity squared, the expectation squared. This expectation of the square minus the square of the expectation. Hopefully you remember that back from when we talked about variance. Now, if I write out this expression, now I just calculated this. This was equal to E. So this term here is just going to give us E squared. This term is going to give us E squared. So that's easy enough. Let's work with this term then, the expectation of the Hamiltonian squared. This is again going to be an integral, and I'll drop the time-dependent parts here. Actually, you know what? I'll drop all of this. We don't need to actually express everything as an integral. You know what's going to happen in this integral. The expectation of any operator is the integral of psi star times the operator times psi, integrated over the domain, in this case x. So if I substitute the Hamiltonian squared into this, in the context of the discussion we've had over the last few minutes about how the time dependence drops out, what we're effectively going to end up with, needing to consider, is this. And this is going to end up looking like h hat squared times just the spatial part, x. Now h hat squared times the spatial part x, well that's h hat times h hat acting on h hat acting on x. It's the definition of squaring an operator. You just apply the operator twice. Now, as before, I know this. This is E times x, since I know x satisfies the time-independent Schrodinger equation. So this is going to be h acting on E x. There's nothing special about E, it's just a number, so I can pull it out. The Hamiltonian operator won't do anything to that number. And I'll just be left with E and h hat acting on x. Well, again, h hat acting on x, that's E times x. So I'm going to end up with E squared times x. Now back in the integral equation, this E squared, just being a constant, can be pulled out front. And what we would end up with is E squared times the integral of x star x dx. And again, if we've properly normalized this, this will just be 1, and we'll end up with E squared. So, this is interesting. What we got for our expectation of Hamiltonian squared was E squared. So what this tells us is that sigma sub h hat squared our variance, or our squared uncertainty in the energy of the system, is equal to E squared from this term minus E squared from this term, which is 0. Stationary states like this that solve the time-independent Schrodinger equation have energy given by the separation constant E and no uncertainty in energy. They essentially have exactly E amount of energy. What exactly does that mean? Well, we'll talk about that in a moment. Just to summarize things, for these stationary states, the probability density has no time dependence. The time-dependent part cancels itself out when you're calculating the probability density. Expectation values of any operator that we're going to be concerned with in this class also have no time dependence. And the energy is specified exactly that separation constant E in, for instance, the time-independent Schrodinger equation h hat x equals E x. This is our energy. That's nice, it has some physical significance. But there's not going to be no uncertainty in energy. These states have defined energy and it's exact, which means if we measured the energy of the system, we would always get the same thing. Now, just to comment very briefly on what that actually means. What does it mean for a system to have no energy uncertainty? If you remember back when I talked about the difference between quantum physics and classical physics and where the boundary between classical and quantum physics fell, well, I gave you an energy-time uncertainty relation where the uncertainty in the energy and the uncertainty in the time always had to be greater than about h bar over 2. Now, what does that mean if we have no energy uncertainty? Well, delta E is 0. So 0 times something, it has to be greater than h bar. Now, h bar is really small, but h bar is not 0, so there's mathematically some problem here. And what actually happens is that delta T has to be infinity. What does that mean? Why is that a meaningful statement? Well, essentially, this delta T here in the energy-time uncertainty relationship tells you about when the state exists, the duration of the process. Essentially, it's the answer to the question, how accurately can you tell me when this state exists? And for something like a stationary state, it always exists. There's no time dependence. You could run the clock backwards, you could run the clock forwards, all the way before the beginning of the universe, technically, since none of that beginning of the universe stuff is covered in this course. Essentially, this state always exists. So the answer to the question when, well, always, whenever you want, forever, however you want to put it. Essentially, these stationary states always exist. They have no time dependence and they're constant forever. Now, that's not the most realistic state in the world, but they are the sorts of things that we get from the Schrodinger equation, and they actually have some really, really nice mathematical properties that we'll start talking about in the next lecture and in the lectures after that. But that's a stationary state for you. It's a result of the solution to the time-independent Schrodinger equation, possibly with the time independence added back on, depending on how sloppy I am being with my notation at any given moment. Stationary states are really important, and they have some very nice mathematical properties. To preview a little bit, if you know the stationary states of your system, you know everything about the system, and you can find the answer to any question you might possibly ask about the quantum mechanical behavior of your system. Kinetic energy, and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, part. what does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi, so we're still moving toward solutions to the Schrodinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrodinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic. Really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrodinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, e to the, minus I times e times t divided by h bar. So this is our time evolution part, and this is our space